Okay, so let's rediscuss the concept of a Jordan normal form. But this time we will do this on the basis of generalized eigenvectors. Okay. Um, in the previous lecture on Jordan forms, we had discussed what Jordan blocks are and how do we get Jordan blocks. Um, this lecture will be solely dedicated to this, or if I won't be able to finish the discussion in one lecture, I'll take one more lecture. But the lectures are solely dedicated in finding out a basis, or at least set some tools to find out a basis, which will serve as that very ordered basis of the vector space on which we will be working. The matrix of a linear operator with respect to that basis will be the Jordan normal form. Okay, so typically this will gradually relate you to the concept of similarity from a mathematical point of view. For example, we know that if A is a matrix, then we say A is diagonalizable, right? We say A is diagonalizable. Now, what is the very simple definition of A being diagonalizable? We say that there you have a matrix D, or you can think of it by saying that um, A is similar to a matrix which carries all the eigenvalues of A along its diagonals, right? Let this be D. So we say A is similar to D. What is the other way of saying A is similar to D? We say that there exists uh, invertible matrix. There exists an invertible matrix P such that A is equals to PD P inverse, or we can say that P inverse AP is equals to D, right? And recall that this matrix P, the matrix P, in the matrix P, the columns were vectors, say v1, v2 till vk, where each vi was an eigenvector corresponding to lambda I. Moreover, these vectors, they actually form a basis, an ordered basis for v, right? Right. So the matrix of T with respect to this basis. So this indeed forms the diagonal matrix T. That is right. Recall if you have, if you had eigenspaces, say Wi, where Wi is the eigenspaces, eigenspace associated with the eigenvalue lambda I, then we used to form the basic ordered basis of Wi, right? Suppose Bi is the ordered basis of Wi, then we used to arrange these Bi's in columns, right? So B1, B2 till BR, let's say. This serves as an ordered basis for the vector space V. Okay, and the matrix which the columns of which are these basis elements, it serves as this matrix V. Right? This happens solely because the vector space V, if the linear operator T is diagonalizable, then this vector space V can be decomposed into direct sum of certain T invariant subspaces, and these T invariant subspaces are basically the eigenspaces, right? In this case, when V is diagonalizable, what basically happens is that V is decomposed into the direct sum of each of these eigenspaces, right? Right. Clear? Now, obviously, every matrix is not diagonalizable. So, if every matrix is not diagonalizable, then what we try to do is that if we are given a certain matrix and we find out that it's not diagonalizable, though we need to study it out, we try to come up with another simple form for that matrix, which helps studying the matrix or the operator, linear operator, which is associated with the matrix easier. Okay. And so Jordan form or Jordan normal form, it is one of the simple forms of which we can acquire out of a matrix of a given matrix. Supposedly, if it is not diagonalizable, because if it is diagonalizable, then a diagonal matrix is the most simple form which we, which we can favor for studying. So if you are given a matrix which is not diagonalizable, then Jordan normal form comes out to be, you can think of it as the next immediate simplest form for that matrix, which obviously helps studying it easier. Now the point is that when is a matrix or a linear operator defined on a finite dimensional vector space not diagonalizable. So the sole reason when the linear operator defined on a finite dimensional vector space is not diagonalizable is that the basis elements which you take from each of these eigenspaces, each of the eigenspaces which is associated with that very linear operator, they do not they are not enough to give you an ordered basis for the vector space V. Okay, that is, suppose you have here k eigenspaces, and you take the basis elements from each of these eigenspaces. So you get b1, b2. So you have, suppose B you form out of these basis elements where each of these are basis to wi's. Suppose dimension of V is n. Suppose dimension of V is n. But this very set, this does not have any elements. This does not have elements. If this set would contain n elements, then the linear operator T will immediately be diagonalizable, right? Because of this form. It's very obvious. Because then we have formed out a basis out of the basis elements of the eigenspaces. Okay, but what if the basis elements from when you have extracted it out from each of these eigenspaces are not sufficient enough to form an ordered basis for the vector space V. So in this case, what we try to do is that, so obviously the matrix associated with the linear operator which we'll be working with is not diagonalizable, right? So what we try to do is that we try to come up with certain vectors which are not exactly eigenvectors, but they are somewhat similar to how eigenvectors look or how eigenvectors work. Okay, and using those very vectors, we will complete this basis. On completing this basis, when we have so we will get a basis for V where every element is not exactly an eigenvector. Some of them are eigenvectors, others are basically somewhat similar to eigenvectors, not exactly eigenvectors. So this basis will give you a matrix, obviously for a linear operator, which will not exactly be a diagonal matrix, but it will be somewhat very similar to a diagonal matrix and almost as simple as a diagonal matrix. Okay, and that matrix which we will eventually call the Jordan form of a matrix. Okay, so these things we know, right? That number one, if you have a finite dimensional vector space, okay, let V be a finite dimensional vector space over a field, let's say F. Okay, now for some scalar C, a non-zero vector is said to be an eigenvector. This we know, is said to be an eigenvector associated with the scalar C for a linear operator T, which is defined obviously on V, if T of lambda is exactly equal to C times lambda. Okay, that is, this vector lambda is just scaled by a constant C, by a scalar C, by the operator T. Okay. In this case, lambda is called the eigenvector associated with this value C. This C is called the eigenvalue for T. Okay, this thing we know. Okay. So what I was just saying is that if obviously we can form eigenspaces from it, eigenspaces are the set of all eigenvectors associated with some fixed eigenvalue. That very set will obviously have some basis. Considering those bases, we can form an ordered basis for the vector space V. Suppose we do not get enough elements to form a base or form a standard ordered form an ordered basis for V, then we try to use elements which are very similar to eigenvectors, not exactly eigenvectors, in order to extend the collection to form an ordered basis for V. And these elements are called the generalized eigenvectors. Okay, so definition. So a generalized eigenvector with eigenvalue, or you can also say associated with the eigenvalue, let's say lambda. We are considering this in this definition as well. Okay, so with eigenvalue lambda in F for a linear operator T defined on V. So this is the collection of all linear operators in V, if you recall. Okay, so it is a non-zero vector. It is a non-zero vector V, capital V, such that T minus lambda I to the power K V is 0 for some K greater than 0. For some K greater than 0, and K is the smallest positive integer. K is the smallest positive integer D such that T minus lambda I to the power D of V is 0. That is, K is the smallest positive integer to happen so. Okay. This K is called the exponent of this generalized eigenvector V. Okay, this K is called the exponent of the generalized eigenvector. I should use the term of the generalized eigenvector V. Okay. Further, it is very obvious that if K is 1, then V is a eigenvector. Okay. Eigenvector associated with lambda. Clear? Clear? Okay. So this is the very concept of a generalized eigenvector. Okay. So, okay. So now we come up to a proposition related to these eigenvectors, and these propositions will lead to what we call the Jordan decomposition theorem, which typically says that if you choose any matrix, let's say over an algebraically closed field F, then the matrix is similar to a Jordan matrix, or the matrix has a Jordan form. That is, it has Jordan blocks in a certain block diagonal representation of that matrix. Okay. Now we know. Let me just give a brief reach to it. We know that if a matrix is written in this form, A1, A2 till AK, each of these are blocks, matrix blocks, then we say that this matrix A is a direct sum of these matrices. So the Jordan decomposition theorem in some way means that every matrix is a direct sum of Jordan blocks. Okay. Or every matrix is similar to some matrix which is a direct sum of Jordan blocks. You can typically think about it like that. Okay, let's come back to the proposition. We name it proposition 1. So let X be a uh, okay. Let V be a finite dimensional vector space. Let V be a finite dimensional vector space, and let T be a linear operator defined on it. Okay. One thing I should make it clear here: to define the concept of an eigenvector or to define the concept of a generalized eigenvector, we do not need the vector space to be finite dimension. Okay, that is, but I have a, we are continuously studying finite dimensional vector space for so long. I built a habit of writing it everywhere. Okay, the existence of eigenvectors are not really dependent on vector space being finite dimensional, and obviously that carries for generalized eigenvectors as well. Whatever. So let V be a finite dimensional vector space and T is a linear operator defined on it. Let X be a generalized eigenvector. I'll often use this abbreviation GE for T with exponent D. With exponent D. Okay. And associated to the eigenvalue lambda. Associated to the eigenvalue lambda. Okay. Now for j greater than or equal to 0, we define certain vectors uj as t minus lambda I to the power j of this generalized eigenvector x. Okay. Then obviously ud will become 0, right? Because x has exponent t. We consider a set which consists of the elements u0, u1, u2 till ud minus 1. Okay. And let x be the span of B. Let x be the span of B. Okay. Then x is T invariant. Then x is T invariant, and B is a basis. B is a basis for x. Okay. Now, obviously, by definition, these elements from B are elements from this vector space V, because x is a vector from V. T is a linear operator defined on V. T minus lambda I, any power of T minus lambda is also a linear operator defined on V. So uj is indeed a vector from V. So x is typically a T invariant subspace of V. That's quite trivial, so I have not mentioned it here. Okay. Okay. So we need to prove it, but proving it requires let's discuss another lemma along with this proposition. We name this as lemma 1. Okay, what does this lemma say? So with uj defined as in proposition 1, let y be a non-trivial linear combination of these uj's starting from uj to be, so fixing some index j. Okay, so I'm writing it as cj uj, cj plus 1 uj plus 1, so on and so forth till cd minus 1 ud minus 1. Okay, where j is less than equal to d minus 1 and cj is not equal to 0. Okay, then y is a generalized eigenvector. Then y is a generalized eigenvector associated with same eigenvalue lambda and has exponent d minus j. Okay, so let's check the proof of it, and after proving this, we will prove the proposition 1 as well. Okay. Okay. First thing first, we have the exponent of x to be d. Now we are obviously relating lemma 1 and proposition 1 throughout these set of statements. So we have x. So x is a generalized eigenvector with exponent d. With exponent d, and that typically means from definition that t minus lambda I to the power d is equals to of x is equals to 0, and d is the smallest positive integer to happen. So, and t minus lambda I to the power d minus 1 of x, it will obviously be non-zero, right? So that typically means, so now by definition t minus lambda I to the power d minus 1 of x, that is typically ud minus 1. So ud minus 1 is non-zero, right? ud minus 1 is non-zero. Okay. Now you have y as cj uj plus cj plus 1 uj plus 1 and so on and so forth till you have here cd minus 1 ud minus 1. Then what can you say about t minus lambda I to the power d minus j minus 1? Okay. So this is typically, so these scalars will obviously won't be affected by this linear operator. This is typically a linear operator, right? So it is t minus lambda I to the power d minus j minus 1, right? And it continues till you have here cd minus 1, of uj, right, of uj, and here you have cd minus 1 t minus lambda I of d minus j minus 1 of ud minus, right, of ud minus. Now what is uj by definition? So uj by definition is t minus lambda I j of x, right? What will be the next term? So next term is cj plus 1 t minus lambda I d minus j minus 1 t minus lambda I j plus 1 x, and so on. We will have here cd minus 1 t minus lambda I d minus j minus 1. So u is t minus lambda I, so this is d minus 1, and you have here x. Now obvious, then this is cj. Now so this immediately becomes t minus lambda I to the power d minus 1x, right? Exponent rule, obviously you can relate it. This becomes, if you carefully observe, this becomes t minus lambda I dx, and then the exponent will obviously keep increasing. So here you have c d minus 1 t minus lambda I, so this is 2d minus j minus 2, and you have x here. Whatever, this is greater than d, this is immediately greater than d. So this is ud minus 1, right? So you have cj ud minus 1, and all these elements are 0, right? So this is simply cj ud minus 1, that is again non-zero, as cj is non-zero and ud minus 1 is non-zero. This we just observe ud minus 1 is non-zero. Okay, I have missed here writing y. Okay, c t minus lambda I d minus j minus 1 of y, sorry. But what can you say about t minus lambda I to the power d minus j of y? Then that will trivially be 0. You can just expand it out using whatever I did here. Okay, so in this case this one won't be there, so this j and j cancel out, so you will get d here, and all the other exponents will keep increasing, so this becomes 0, and all the other terms after that will also become 0. So immediately it becomes 0, right? So therefore d minus j is an integer. J minus 1 is obviously, sorry, j is obviously less than or equal to d minus 1. J is indeed less than d. Therefore d minus j is some sort of a positive integer. So there exists a smallest positive integer such that t minus lambda I to the power d minus j of y is 0. So that immediately means y is a generalized eigenvector. Is a generalized eigenvector, and lambda is obviously the eigenvalue which we started with working. So y is a generalized eigenvector associated with lambda with exponent d minus j. Clear? Clear? Now we come to the proof of proposition one. Proof of proposition one. One thing which you can obviously observe, what is the value of t uj? Okay. So what is uj? So this is t times t minus lambda I to the power j of x by definition, right? By definition. Okay. But what can you say about this linear operator? Now observe that you can write it as t minus lambda I. Now see, both of these are linear operators on t, right? You can think of this as the polynomial p of x equal to x, and you can think of this as as another polynomial, say p of x equals to x minus lambda whole to the power j. So typically, so q. So this some sort of pt, and this is some sort of a qt form. In typically speaking, that both are sort of some polynomials related to these linear operators, and considering the same linear operator t, they will obviously commute, right? There is no problem in the commuting. That is what I actually mean to say. So we can write it as t minus lambda to the power j, and we can write t as lambda x plus t minus lambda I of x. Yeah, we can do this, right? Because lambda I of x is lambda x, so lambda x and this lambda x cancels out, correct? Yeah, we can write it like this. Then how can we can just expand it out? So this becomes lambda times t minus lambda I jx plus t minus lambda I to the power j plus 1 of x, right? So this is typically lambda uj, right, plus uj plus 1, right? So this happens if j is less than d minus 1, right? What happens if j is equal to d minus 1? If j is equal to d minus 1, just simply this part becomes 0. And if j is greater than equal to or greater than d minus 1, then this part also becomes 0. And that is solely because of the fact that x is a generalized eigenvector with exponent d. So therefore, what can we say about the images of t uj? So it is simply lambda uj plus uj plus 1 when j is less than d minus 1. It is simply lambda uj if j is equal to d minus 1, and it's 0 if j is greater than d minus 1. Clear? Like clearly, the image of each of these uj is some linear combination of the elements of B from proposition 1. Hence it is in X. Uj itself is in X, obviously, because X is spanned by B, a uj is an element of B. Therefore, if you choose any element from B, if you choose any element from X, since X is a span of B, it is some linear combination of these elements uj's itself. So considering a linear operator defined on, considering an image of any element chosen from B under T, it will actually depend on image of each of these elements from the set B, right? So now each of these elements uj, the image of each of these elements under T is some linear combination of the same set of elements again, right? So if you choose any element x from capital X, X is some linear combination of these uj's, right? So it's, let's say it's sort of aj uj. So we had j equal to 1 to n, right? 1 to d. No, we had j equal to 0 to d minus 1, correct? Right? So what is t of x? So t of x is summation j equal to 0 to d minus 1. It's aj t of uj. But t of uj is again linear combination of the same set of elements uj. So indeed, t of x is again a linear combination of these elements uj's. Hence, x is again in the span of these elements uj's. Hence, that means t of x is inside x again. So clearly, for all small x in capital X, T of X belongs to capital X, since each uj is a linear combination of the elements of B. Sorry, each Tuj is a linear combination of the elements of B or 0, right? Therefore, X is T invariant. X is T invariant. Moreover, what does lemma 1 say? Lemma 1 say that if you choose any non-trivial linear combinations of the elements Uj's, then the coefficients come out to be 0, or they come out to be linearly independent. So obviously, lemma 1 says that any non-trivial linear combination of the elements in B is again a generalized eigenvector, hence non-zero, which implies B is linearly independent, right? Right? Okay. What is an immediate corollary of this? Like obviously, when we have studied generalized eigenvectors, I have already mentioned that they are associated with the eigenvalues of T indeed. But you can sort of speak up about the fact that the eigenvalues we are speaking in terms of the generalized eigenvector are same as the eigenvalues we speak when we discuss our standard eigenvectors. Okay, now that can be an immediate corollary of this due to the fact that if x has exponent d, then the vector ud minus 1 forms an eigenvector with eigenvalue lambda. Okay, with the notation we have used in proposition 1 and proposition for 1 and lemma 1. Okay, whatever, our most important fact is that we have formed a basis. We have a basis B, which is u0 u1 till ud minus 1 in terms of a linear operator T, right? Such that we have T of uj written as it's lambda uj plus 1 if j is less than d minus 1. It's lambda uj if j is equal to d minus 1, and it's 0 if j is greater than d minus 1. Now my question is, suppose this basis or this set, now we have just proved the fact that if we consider a set which is a span of these elements of B, then that immediately in that case B B acts as the basis for that set. So suppose let's say V is a span of these elements in B. Okay, that is, it is a span of the elements u0 u1 till uj plus 1. Sorry, very sorry, ud minus 1. ud minus 1. Okay. Now we have just seen that in that case, this B acts as a basis for V. T is a linear operator defined on V. Let so suppose this is star. Let T be a linear operator defined on V satisfying star. Then what can we say about the matrix of T with respect to V? Okay, that is my question, and you can easily observe what is happening here. So what is we can just simply talk about one or two of these eigenvalues. What is T of u0 from here? So T of u0 is lambda u0 plus u1, right? And that is 0 times u2 and so on and so forth. It's 0 times ud minus 1, right? What is T of u1? T of u1 is lambda u1 plus u2. All the other elements are 0, right? 0 times ud minus 1. Here you have 0 times u0. If we continue, what is TUD minus 1? So TUD minus 1 is it's lambda times ud minus 1 and all the other elements. So it's 0 times u0 plus 0 times u1 plus 0 times u2 and so on it continues, right? Now we know how we form matrices out of the images of the basis elements. So the matrix of T, we just arrange the coefficients column wise, right? So matrix of T with respect to B, how does it look like? So we have lambda, right? We have lambda here. Then we have 1 here, right? So we have 1 here and all the other elements are 0. Then we have 0 in the first place. We have lambda here. We have 1 in the immediate next position in the column and all the other elements are 0. And obviously this trend continues. So we have 0 here, then lambda here, then 1 here and all the other elements are 0. So the diagonal completely consists of lambda, which is again evident from this, because this is the d minus 1 d minus 1 position. The complete diagonal contains the elements lambda and the super diagonal entries are ones, right? Right. So we have the diagonal completely consisting of the eigenvalue lambda and the super diagonal completely consists of the value 1. Okay. This very matrix is called the Jordan block associated with the eigenvalue lambda, and often this is denoted as J lambda. Clear? Okay. In some books you can also find the Jordan block J lambda. It is denoted like this: lambda, then you have 1 here, then 1 here, then 1 here and so on. So the 1 comes above these lambdas from some point of view. And how does this happen? So there is nothing much typical there. We just revert the basis. What we typically do is that, so you can observe, you can write TUJ like this: uj plus 1 plus lambda uj, right? Or I'm not speaking about this in this case. Suppose we start in the basis, we start with the element uj, ud minus 1. Okay, so B starts with the element ud minus 1. Okay, I'm arranging them accordingly. Then what is TUD minus 1? So TUD minus 1 is typically it's lambda ud minus 1, right? It's lambda ud minus 1, right? What in that case, what typically happens is that we consider the linear operator, or rather I should say we consider the vectors uj in such way that T of uj, it comes out in this form. It comes out as uj plus lambda uj plus 1. Okay, so you have uj, I mean, so in that case what you have u2 as. So u2 you have, sorry, this is u1, right? This vector corresponds to u1. So in case of u1, what you have 1 times u0 plus lambda times u1. Are you getting my point? So this is uj minus 1 and this is uj, correct? Okay, uj. So you set the vector elements in such a way that this is the criteria which is obeyed. Okay. So in that case the Jordan normal form comes in this way, but it doesn't matter. You can consider this way of writing it, this way of writing it, whatever it suits you. Okay, is it clear? So, so this is typically what a Jordan block is. Okay. Now, um, let's just see an example. So suppose you have a Jordan block for the eigenvalue 0, and you consider, let's say, the 2 cross 2 Jordan block. Okay, suppose you consider the 2 cross 2 Jordan block, which is 0 0 1 0. I guess now it's obvious. And consider this to be the matrix of a linear operator T defined on, so let's say defined on C2. Okay, so C2 is obviously a vector space over C. So the standard basis of C2, it exactly consists of the elements 1 0 and 0 1. So let this be E1, let this be E2. How does J0 act on E1? So obviously J0 of E1 is 0 0 1 0 times 0, times 1 0. So what does it look like? So it's 0 times, so first element is 0, second element is 1. It is exactly E2. And what is J0 of E2? I mean J0 acting on E2. So it's 0 0 1 0 times 0 1. We'll see that it comes out to be the 0 matrix. 0 vector, I should say. Inductively, if you consider the uh, the Jordan block associated with the eigenvalue 0, so consider this as the D cross D Jordan block associated with the eigenvalue 0. Then if you consider this as a matrix, as the matrix of a linear operator defined on, say, CD, then the way this J0 acts is, it acts as J0, this sends E1 to E2, E2 to E3, E3 to E4, and so on it continues till you reach ED, and then it sends ED to 0. Okay, all these observations will be connected after we study the Jordan decomposition theorem. We're not going to study the Jordan decomposition theorem in this lecture because it's already a 42-43 minutes lecture. We will just end this lecture by stating what the Jordan decomposition theorem typically is. So let A be a complex n cross n matrix. That was the thing which we were speaking previously, that we need an algebraically closed matrix so that we at least have all the eigenvalues of it in hand. Okay. The so the Jordan decomposition theorem, typically says that every n cross n matrix is similar to a matrix J, such that J is a block diagonal matrix. J is a block diagonal matrix with the blocks being Jordan blocks. With the blocks being Jordan blocks, that is, so you can think of J as this block. Say it's J1, J2, so on and so forth till say some JL, where each Ji is a Jordan block associated with some eigenvalue lambda I. Okay, and the dimension of each of these blocks Ji's is some D is let's say Di cross Di, such that the summation over these di is equal n, where n is the dimension of V. That's quite obvious. Or dimension of A, you can think of it like that. This Jordan block has a very important characteristic that if the the dimension of each of these Jordan blocks ji's is di, this actually happens when the characteristic polynomial of j is of the form fx equals to x minus say lambda I to the power di. So product of this, let me write it as a product of this. Okay. So typically speaking, if you have an eigenvalue which has algebraic multiplicity di, then the Jordan block associated with that eigenvalue is of dimension di. That's typically speaking. Clear? Okay. And a diagonal form of a matrix or diagonal matrix associated with some eigenvalue is also a Jordan form. Okay. What I'm trying to say is that what are the all 3 cross 3 possible Jordan forms? 3 cross 3 possible Jordan forms. Okay. So one is simply say when it's a diagonal matrix, that is it's lambda, so lambda 1 lambda 2 0 0. Then we will obviously have a, sorry, we are talking about 3 cross 3 Jordan matrix, right? Sorry. Okay. So if you have lambda 1 lambda 2 lambda 3, this is one possible Jordan block. What can be the other possible Jordan block? Jordan form. Suppose you have a 2 cross 2 block and a 1 cross 1 block. Suppose you have lambda, a Jordan block associated with the eigenvalue lambda. Okay, so let me just mark it like this. And you have suppose this is lambda 1. And you have a singleton Jordan block lambda 2. 1 cross 1 Jordan block. All these elements are 0. But in the other form, so observe that these are all 1 cross 1 blocks, nothing else. These are all 1 cross 1 blocks. This is a 2 cross 2 and 1 block. The other possible is if the complete 3 cross 3 matrix is of a single block. So it will obviously be of this form, right? So it will be of the form lambda. You have 1 here, you have 1 here. All the other elements are 0. Right? So here you have a 2 cross 2 and a 1 cross 1 Jordan block. Here you have 3 1 cross 1 Jordan blocks. And here you have a 3 cross 3 Jordan block. Right? Is it clear? The characteristic polynomial of this is typically x minus lambda 1 into x minus lambda 2 into x minus lambda 3. Observe, it's quite obvious from here that the minimal polynomial splits into linear factors. Question is, what can we say about the minimal polynomial of this Jordan form and this Jordan form? We'll try to discuss those concepts in the next few lectures. Okay. Meet you guys in the next lecture.